Auzubillahiminash-shaytanir-rajim. Bismillahir-rahmanir-rahim. Dear students, today first of all we have a definition. If X is a non-empty subset of a group G, then the set of all the elements of G that are permutable with X is called the normalizer of X in G and is denoted by NGX. That is, NGX is equal to G belong to G such that GX is equal to XG. Note that it is not necessary for the subset X and normalizer of X in G to commute element by element, but their commutation is required as a subset. Also note that the normalizer of X in G constitute a subgroup of G. To prove this, let AB belong to the normalizer of X in G. Then by definition, AX is equal to XA and XB is equal to XB. So this implies that B inverse X is equal to XB inverse. Now AB whole inverse bracket X is equal to AB inverse X is equal to AXB inverse is equal to AXB inverse. So AB inverse XB AB inverse is equal to XAB inverse. That is AB whole inverse into X is equal to XAB inverse. This implies that it takes the commutative property with the X. So this implies that AB inverse belongs to the normalizer of X in G. So we have again definition. An element of a group G is called a conjugate to an element A belong to G if there exists some element G belong to G such that B is equal to G inverse AG. Next, we observe that each element A belong to G is the conjugate to itself, because for any A belong to G we can write A is equal to A inverse A1 where 1 belong to G. Moreover, if B is equal to G inverse AG, then A is equal to GBG inverse. So A is equal to G inverse whole inverse BG inverse, A is a conjugate to B. And if B is conjugate to A, then A is conjugate to B. This implies that if A is conjugate to B, then we write A is conjugate to B and B is conjugate to A is conjugate to B. The relation, this is called conjugacy relation. The collection of all the conjugate of an element A belong to G is called the conjugacy class and is denoted by CA or CA bar, that is CA is equal to X belong to G such that A is conjugate to X is equal to X belong to G such that A is equal to GXG. This implies that the relation, this indicates a partition of the set G into the equivalence classes. The elements in the same conjugacy class are called conjugate of an element one another. We have next theorem, prove that conjugacy is an equivalence relation on a group G. Proof. Now let G be a group. To prove the required result, we will prove that conjugacy of an element is in G reflexive, symmetric and transitive. For each A belong to G, when we can write A is equal to A inverse 1A, hence each A belong to G is conjugate to itself, so conjugacy is reflexive. Number 2, if B belong to G, B conjugate and A belong to G, then by definition there exists an element G belong to G such that B is equal to G inverse AG, then A is equal to GBG inverse. This implies that A is equal to G inverse whole inverse BG inverse such that A is conjugate to B. Thus symmetric property is satisfied. Now if A is conjugate to B and B is conjugate to C, then we can prove that A is conjugate to C. Now since A is conjugate to B, so by definition there exists G1 belong to G such that B is equal to G1 inverse A G1. Also since B is conjugate to C, so by definition there exists some G2 belong to G such that C is equal to G2 inverse B G2. Now C is equal to G2 inverse B G2 is equal to G2 inverse G1 inverse A G1 G2 is equal to G1 G2 whole inverse A G1 G2. So this implies that A is conjugate to C, that is A is conjugate to C, hence the conjugacy is an equivalence relation. That is our required.